Hi, welcome to Tea Leaves Programming. Today we're programming like it's 1979. Haskell for Dilettantes, Part 3. Today we're actually going to be doing a lab. We're going to do the first homework in the CIS 194 class created by Professor Joachim Breitner. Now, one thing I do want to note that I did not realize when I made the first and second videos in this series is that Professor Breitner has actually adapted his class into a web page called Haskell via Sokoban. And this might be a better start for someone who wants to just kind of power through, start at the beginning, go straight to the end. The material is largely the same, so I could course correct and use Haskell via Sokoban for Haskell for Dilettantes instead. However, I actually want to continue to use CIS 184 for a very selfish reason, which is that this series is a series. I have a day job. I only have so much time to do this these videos, and so the class actually divides this up really nicely. Whereas Haskell via Sokoban is kind of this long continuous string of material. So we're going to continue with CIS 194. If you would prefer to do this work via Haskell via Sokoban, it's the same material, largely. It's just broken up a little bit differently. So what are we doing here? Well, we're going to look at homework 1. And anything that has to do with Piazza or with submitting the homework, you can ignore that because we're not taking a class at the University of Pennsylvania. We're just a bunch of nerds on YouTube having fun. All right, exercise 0, done. We get to skip it. Exercise 1. So they mention this traffic light animation, and that is this animation we see right here, alternating between red and green. And what they want us to do is to change the code to include the yellow light and animate a correct sequence of traffic light signaling, a long green phase, a short amber phase, a long red phase, and then a short red and amber phase, and then back to green. And there's a footnote here saying that this is the traffic light phase for Germany. So for my 1 or 2 German viewers, this is your moment. And the resulting program should be called Exercise 1. So let's look at the code. We're going to be doing all our work in Code World, or code.world today. So no Emacs, no shell, other than whatever shell we can get out of Code World. So what have we got here? We have some boilerplate code. What does all this stuff mean? These are options that tell the Haskell language how to behave. We import the Code World API. As you use code.world, you may want to know some details of the API. The easiest way to get to it is to just click Guide, and that will open a frame. You can open a new tab, which I've actually already done, and that will help you walk through the various functions and data structures that are available to you in Code World. This is also available on Google, the Haskell API site. If you search for Code World, it'll bring you to the package, and you can click here and you get a similar page. And this will be useful when we leave the environment of code.world and maybe start using the Code World API from our own text editor and command line. All right, so let's have at it. Let's jump right in. So we need to change this to have 3 lights, not just 2. And we need to change the sequence of the animation. So I kind of love this as an introductory exercise because here is all the code for exercise 1. Largely in this series, we're going to be filling in these exercises and replacing things that are undefined. This exercise doesn't work that way. In fact, there's nothing here that's undefined. So instead of writing our own code, we're going to be modifying code. As a longtime hacker, as a longtime developer, you know, for me, one of the worst moments of writing software is opening a blank editor window. And so I love that for the first exercise, we've removed that. The tyranny of the blank editor window, not here. We're just making changes. And in fact, one of the first programming projects I did as for myself was, I remember we used to have a game on Unix systems called uRogue, Ultra Rogue. If you've heard of the original Rogue, this was kind of an elaboration of Rogue with a lot more details and a lot more modifications by a guy named Herb Chong. And we had the source code, and I wanted to make changes, and it was a lot of fun doing it. It made programming seem maybe easier than it actually is, but that's okay. So let's just try to understand this code a little bit before we start changing things. So main is the entry point here, and we can see that main is calling, all it does is call one function, exercise1. Main is equivalent to exercise1. And we can see that exercise1 is down here on the bottom. It's of type IO, and it is calling animation of traffic light animation. Okay, well, traffic light animation we see right here. That's a function that we defined. We can see that it takes a double and returns a picture. What's this animation of? That is part of the Code World API. And we could go and read the description here. In fact, why don't we do that? Let's read the documentation together. Animation of goes from double to picture. When I say goes from, what I mean is, just to be really explicit, it takes a double as input and it emits a picture as output. Another way to put it is, and we can see I've already made my first mistake. I misspoke. It does not take a double and return a picture. Rather, it takes a function that takes a double and returns a picture. And then given that function, it returns IO. It causes a side effect. In this case, the side effect is everything we see here in the window which is running. It causes the animation. It's pretty simple or pretty easy to get lost in the maze of this syntax. And I just did it just starting out. That's why this is Haskell for dilettantes and not Haskell for experts. Those of you who've been following the channel know I love looking for the opportunity to make mistakes because mistakes are how we learn. So now what we've learned is we have to be very careful when we read our type signatures. All right, let's try that again. So animation of traffic light animation takes a double and returns a picture. All that does is call traffic controller with no arguments. So logically, I expect traffic controller to also be a function that takes a double and return a picture. And sure enough, here it is. Now, the thing that I want to call out here is so far, I'm mostly looking at the types. I'm not really looking at the actual code. Traffic controller is where we're going to start looking at the code. All right, traffic controller T. T is our double, right? This is an argument to this function, traffic controller. So this is a number, a floating point number, essentially. And we've got some math here. We're going to round it, take mod 2. And if that mod 2, number divided by 3 mod 2 is 0, then traffic light true, otherwise traffic light false. Well, what does traffic light true false do? That takes a bool and emits a picture. Okay. Traffic light true, if the bool is true, then we're drawing green and black and the frame. So this ampersand is, I believe, a Code World function. Let's see if I could find it in our documentation. There it is. So it's an operator which takes, given two pictures, returns a third picture, and it's just composing them together. What you'd expect an ampersand to do in this case. And then if traffic light is false, then we're getting this red picture. True, false. And we're doing it with some timing. And we have a frame that is some size. And then let's look at these. So we're composing, let's just look at the green line first. Bot circle green, bottom circle, top circle, black, and a frame. So since we're changing this, an immediate question is how abstract do we get, right? Like it's kind of like, why are we defining this as the bottom circle, the top circle? We kind of have the position implicitly coded in there. We could imagine abstracting that out a little more. I'm not going to do that. I'm going to try and stay really concrete. And we see here bot circle C, given some argument C, which is a color. Colored C, translated solid circle. So we're going to kind of read from the inside out here. Solid circle 1 is probably the radius. Let's make our first change here. Let's see what happens if we make the bottom circle radius 2. And then I think I have to click run to get that to recognize. Yeah, and our circle immediately gets much bigger. Okay, great. We've made something happen on screen. We've changed a thing. Let's change it back to 1. All right, well, my instinct here, I want to stay super concrete. I don't want to add any abstraction layers. Let's go, I'm going to use some terminology here. If we look at this code, this is the top of the code, and this is the bottom of the code. But if you remember how we went through it, we started in main, we came here, we went to traffic light animation, which is called traffic. I view this in my monkey brain as diving down stack layers. Might be wrong. Maybe your brain views it as building up stack layers. I view it as diving down. So when I say I want to start from the bottom, what I mean is not the physical bottom in my editor. I mean the notional bottom in terms of how my monkey brain is conceiving this code. And I view this right here, draw a circle, as kind of the bottom. And then this is a little closer to the bottom, and this is higher up, etc. So the first thing I want to do, I'm going to add a new circle. Let's do middle circle. So we have now declared that there is a new name, middle circle, which takes a color and goes to picture. You could see we're immediately getting an error message. It's telling me that I've defined a type, but there's no binding. If I were to click run right now, we'd get an error message. In fact, let's do that. And I apologize if I'm going too slowly for some of you. I know that some of you maybe came here from the Haskell Reddit. You're much more experienced than kind of the imaginary person that I'm envisioning who's the recipient for this video. I'm going to go slow. I'm going to take as much time as it needs, and I'm going to try and explain things as we go. And we get the same error message here. And what this means, this error message, is that I've defined something in a type signature, but there's no binding. And we can, for purposes of discussion, view binding as something with an equal sign, taking the name middle circle and translating it to code. So step 1, let's add a binding, and let's have it do nothing. We're going to use that undefined keyword we talked about last time. You could see our warning went away. Can we run this code? Well, it turns out we can. And the reason we can run this code is that there's no code actually calling it. Partially because Haskell is a lazy language, there's no reason to evaluate this code. So as far as the language is concerned, this is fine that we have an undefined function. All right, so we're going to draw a middle circle somehow. Let's worry about it later. Well, we know we're going to need more space for that middle circle, and I'm not quite sure how much. Let's guess that it's 3. This is really not abstract at all, right? Like, you'd really want it to figure out how much space it needs for each circle. But I'm just going to assume, well, you know what? Let's not assume. I was going to assume that this is our x-axis, our width, excuse me, and this is our height. But let's not assume. We're calling an API here in Code World called rectangle. So let's go look at it. Rectangle, a thin rectangle with this width and height. It takes 2 doubles and goes to a picture. I love Code World. I want your opinion on this. This is a very standard Haskell way of writing an API. it is kind of maximally abstract. We have no names for these arguments. It's implied that, well, the first one is probably width and the second one is probably height, but it's not actually stated, right? And if I was writing this documentation, I would probably say the first argument, if I didn't want to put, name these arguments, create like a width type and a height type, which you probably wouldn't, I would say the first argument is width, the second argument is height. Am I being too prissy? Is that a reasonable expectation? My expectation, having seen the Haskell community for a while, is that if I filed that radar against Code World, I know the people who wrote it. They would take it seriously. If they're watching this video, someone is probably filing an issue on it right now. We should update the documentation. These guys are great, and I want to be clear, I'm not trying to throw anyone under the bus. If I filed this issue in GitHub or rewrote the documentation in GitHub for some for some abstract kind of hypothetical Haskell API, it would be a coin flip for me whether someone would reply to that saying, well, it's clear what that is. Why should we name these things? It would be too verbose. Don't explain anything you don't have to explain. So I'd like to know, is that perception of mine correct? Or, should I stop this video now and go file that issue? Anyway, okay, we now know or can infer that this is higher. Note that when we made a change, we don't have to hit save, and Code World tells us your code is no longer the same thing that's running in this playground. And now we can see our rectangle got bigger and our two circles are still in the same position, centered within it. And we can see, looking at the circles, this translated. What does that do? Well, let's go look at the API. Translated. Double, double, picture, picture. So it takes two doubles and a pick. Okay, so these are the inputs and this is the output. Now, part of the reason why those aren't labeled as inputs and outputs has to do with what you'll hear referred to in Haskell circles as the currying of functions. I don't want to get too far down this path because we are going to talk about it when we actually start using partial application. But one of the lies I've already told you is the idea that this function takes 3 arguments and returns 1. In a world where you are using curried arguments, a more accurate way to describe this is that this is a function that takes 1 argument and returns this function. And this function takes another argument, which returns this function. And then finally, this function takes a picture and returns a picture. Kind of nested application of functions. This takes a while to get your head around, and it's very tricky to motivate, honestly, until you have a reason to do it. So I'm not going to do it. And I want to be clear that during this series, I'm going to describe this as this takes 3 arguments and returns 1 argument, even though in some sense it's not true. It's entirely possible in Haskell for us to write our own translated function. Which uses a product type, or a tuple, really a threeple, to do this. Sorry for going silent while I try and get this right. Right. So what did I do here? Well, I wrote a new function. This function really does take 1 argument, 1 argument composed of 3 items, and returns a picture. Takes one argument, returns one argument. In this part of our actual definition, our binding, I'm using pattern matching to decompose this thruple into three separate bindings, X, Y, and image. And then we're calling this original API translated XY image. In fact, we will probably use that API. I'll do it at some point just to show that it's possible. So you can do this. You could write functions that do this. It is not the common style in Haskell for various reasons. That may become more apparent in a future video. All right. All of this preparatory work. So let's go ahead, instead of defining middle circle, let's go ahead and use it, right? Let's say what we want it to be. Traffic light. We're going to deal with this, the fact that this is a bool, in a little bit. For right now, let's just assume we still only have these two states, and the middle circle is going to be black in each of them, right? So we're going to say middle circle black, and we're going to compose it. And in fact, can I do this? I want to break this out a little bit, just so it's easier to read in this narrow screen. Yeah, that works. All right, changes detected. Let's run our code. We know this isn't going to work. That's okay. All right. And we have now hit a runtime error because we called undefined code. It's an interesting philosophical question for a language that is so type insistent that we can have these undefined functions. In practice, it's super convenient. I'm very glad that we can. All right, so now undefined is not good enough, right? How can we make this code work? Well, we could write a middle circle function that does the right thing. Let's do something else. If we go to our Code World API, let's look and see, what do we need? We need something that takes a color and returns a picture. Well, we're already taking a color. We can do whatever we want with that color. Pictures. If we look at pictures, we can see we have all these options, but right up top, a blank picture. All right, so instead of undefined, let's use blank as our definition for the middle circle here. And we may get a warning here because I'm not using this color. Let's see if we get it. We may have turned those warnings off, or Code World may turn those warnings. No warn unused binds. Yes, because of this, we're not getting a warning about this. So we want to bump the top circle up a little bit higher, and we want to bump the bottom circle lower a little bit. We know that our translated function, which we looked up before, does that. Let's add, if we add one on, if we make that one higher and this one lower, that gives us 2. I think that's too much space, actually, isn't it? Yeah, it's not quite satisfying. We may revisit that. Anyway, let's try 8.0. I want more padding on the outside of the traffic light. Or I'm going to stop. I'm going to stop moving this around. We're just, that's what our traffic light looks like for right now. And we can see that it's black, which is what we expect because we're only calling it here. And we can see it's disappearing, right? Like in this case, this false case. Let's go ahead and add it here. Middle circle black and top circle. No. You're going to see a lot of me formatting this code. I apologize. I'm very type A about that. I have a certain way I like it to look. All right, so now we should have that circle drawing in every case. The problem is there aren't really enough cases. And I'm not even thinking of enough cases in terms of animation, like there's on and off, right? Essentially, green is on or green is off, red is on or red is off. So I think we need two things here. We need some way to represent the different states of our traffic light, and we need to modify this traffic light function to use those, to be able to use those states. So whenever you think of defining a bunch of unique states, if there's two of them, maybe using a bool is fine, but it doesn't carry a lot of semantic information. I think we want a sum type. So we're going to use a data declaration here. And let's go back and get our list of phases. And I'm going to paste it right there. All right, so there's two ways that we could look at these states. We could look at them as like one state, right? There's like long green, long red, short red and amber, short amber, back to green. No, actually, so that back to green state, that's not really a state. That's just going back to the beginning. So there are 4 states, and they are unique in terms of their color, right? So we can say, we've got 4 phases, and that needs to be capital letter because it's a type. We're making a new type. It's called light phases. And that type's inhabitants are green, amber, red. We'll say red, amber. You might ask, why don't we like OR these things together? It's because each of these is its own definition, essentially. And then we want to be able to show, I think we want to be, we're not going to print it out actually. So maybe this deriving show is unnecessary and we'll get to it later. Okay. And so if we do that, okay. Let's go ahead and define a new function rather than using our old function. And that's going to take, I call this light phases. That's dumb. Let's just call it light phase. I shouldn't say that's dumb. That's, again, I'm doing the thing. That was an ill-considered name. I should have chosen a better name. We made a mistake. Making mistakes is natural. We fixed the mistake. So we'll call it light phase. It takes a light phase and it returns a picture. All right. So we're getting our warning. It says we don't have a binding. Let's make bindings. And we know we're going to need to use 4 of these bindings. I told you in the previous video that I love using pattern matching, and so I'm going to do it. And I'm going to do it this way. 1, 2, 3. Very similar to what we've got here, right? All right, so first, we can literally, we know that this is the green phase, right? I'm just going to copy paste that code. I have confidence that that code is correct. There's no variables passed in. It's simply used this way. Maximally not abstract. Likewise, we know that this is our red phase. Okay. Our red amber phase is going to look similar. We're not using any of these phases yet, right? We know in this case our middle circle is going to be yellow. I'm assuming yellow is a color. Let's look at the API. Black, white, red, green, blue, yellow, orange, brown, pink, purple, gray, lots of them. There's probably an API here where we can provide, yeah, a hue. Is there one? Yeah, RGB, right. So we could, if we had a very specific amber in mind, we could create our own. And here's the definition of what a color is. It has a constructor, RBGA, and it's 4 doubles. So if we didn't like yellow, we could do, you know, RGBA, and then, you know, that's 255 0, 2 0. I'm assuming that's the, it could be 1.0 actually. Could be. Anyway, I'm not going to worry about that right now. We're going to say yellow. Yellow is good enough for the likes of us. Okay. And then we're going to do the same thing here. Right? Except our middle circle is going to, our top circle is going to be black in that case. And our bottom circle is black, right? Okay. Does anyone else like really get upset when these things aren't aligned and you move them? I'm not going to do it because I'll spend all my time here. Okay, so now we have this completely unused set of functions. Okay, so what are we going to do here? Well, again, I'm going to copy this. I'm just going to call it traffic controller 2. As I said, you would call it traffic controller tick if you wanted to be all Haskell-y about it. 2 is good enough for me. And instead of calling true and false, I'm going to call traffic like phased. And let's keep it the same for right now. All right. And now that we've done this, we could have changed this code, of course. That would have worked fine. But I like having the old code and the new code around while we're working through it. Now, to use the new code, all I have to do really is that. Call this function instead of that function. Let's see if it works. And works here should mean it looks exactly the same. Let's check our phases, though. Let's go ahead and we'll do amber and red amber. There's our red amber, and there's our amber. And that's working. So now all we got to do is change our traffic controller 2 to implement these phases. So we're going to have to do a little math. All right, so we've got long, short, long, short. I am arbitrarily going to decide, and I'm copying this down here so I have it close to where I'm doing my work. I'm arbitrarily deciding that long means 3 units and short means 2 units. Is that correct? Does that actually match Euro lights? I have no idea. You know what? Let's make a short 1 unit. I've got long and short. It'd be nice if I could actually type. All right, 3, 6, 7, 8. All right, first let's put back our green and red phases, right? Let's make this mod 8. Can't remember if it's mod 8 or 7. I guess we'll find out. And instead of saying we'll do it when it's 0, let's say 0, 1, or 2. Let's say it when it's less than 3, it's going to be green. Let's see if that works. So here I expect actually a short green and then a really long red, right? Oh, and here's our T time climbing up. Excellent. Well, what is this? What does that control? Let's see if we get rid of that division. How does this work? Looks like it just makes it a little faster. 7, 8. Okay, I'm going to just use T here for right now, and we can replace that with T divided by 3. Actually, we get to introduce some syntax here. Since I know I want to change this value a few times, but I don't know what it's going to be, and I'm probably going to use it more than once. Let's do this. We're going to use a where clause. All right. So let's add a new case here. We might use another where clause, don't you think? Mod 8, if it's greater than or equal to 3, but less than, I think we said it was going to be 1, less than 4, then we want amber, right? Couldn't match it with, oh, I have to actually call the traffic light phased amber. Actually, I have to call a function. All right, let's see if our amber light appears now. There's our amber light. It was a nice short version, so that worked. But boy, this is starting to look ugly, and we're repeating this a whole bunch, aren't we? Well, we can continue to use our where clause to do this for us. What should we call this? I want to give it a nice name besides like X. I don't like that stuff. Let's just call it segment. Yep. And we can see we're able to use this binding here just fine. And now we can say get rid of all of these uses. Right. And we can define our last version here. If segment is, I think we want our otherwise to actually be red amber. And we're counting up here. If segment is greater than or equal to 4 and segment is less than 4, 5, 6, 7. Yes, I count on my fingers sometimes. Okay, let's see if it works. I'm so excited. Green, nice long segment, short yellow segment, a long red phase, short red amber phase. We're done. That is exercise 1 of homework 1 of CIS 194, which is also kind of the same thing as Haskell via Sokoban. Now, could we do more? Could we do better? Could we make this stuff more abstract? Yes, absolutely we could. But I'm not going to. I think that a fun exercise is actually to take this very concrete solution and ask yourself, how could you make this much more abstract than it is? One thing that jumps to my mind is this just seems super wanky, and we have magic numbers littered all around this code. Is there a way, could I define what is short and what is long and use that as a way of doing it? Absolutely. But we're not going to do that for right now. I think we're going to go on to exercise 2.